So the first question was, um, some of the topics might be sometimes confusing sometimes for me.
Mhm.
So I was going to ask if you could recommend like a precursor textbook to this one. And the second question was relating to the chapters 1, 3, and 4. So far, we've been studying like the variables in single dimension or just a single variable. So we can see like a probability function that looks like a curve for a normal distribution. But what happens when it's like, um, are there scenarios where like when you have more than one variable, instead of being a curve, it looks like a 3D, like a 3D droplet or something else, because like in the first chapter I mentioned something about being like a gravity, like the mean being like the center of gravity kind of thing. So I was just wondering if there's something, what happens if, well, I don't know, what scenarios would you have something that looks like a droplet um or other kinds of shapes or like skews that maybe like uh other kind of 3D shapes kind of thing. Does that does that make sense, like in terms of the question I asked?
I think that's a very solid question that you asked. Like you mean like a teardrop or something like that? Real quick before I answer that. So here's the answer to your first question. I don't know if you can see with my background in the back. This is a book that I would say statistics. Let's take a look through it. It's been a minute since I've used it. Yeah, this will be perfect. Like I don't know if you can see if I can put this up to the camera.
No,
Probably
it blurs it
not.
out.
Yeah, there. So basically, it's called statistics. Here, let me hold it this way.
Okay.
Here, I'll just by
You could,
McClave and Sinsich.
if you
Uh,
could just put the name and the author in the chat, because
I'll do that. I'll do that after we're done. I'll post
yeah,
it to the
great.
Slack channel. Okay.
Because I'd
So
also
Yeah.
read another book than this one, so that's a great.
I'll tell you guys. I'll tell you guys something. I'm not a special case. I know your students and I'm the professor and everything, but this type of work, especially stats and Python, I don't have it memorized. There's things you have to understand, and there's things you have to memorize. So it's one of those things like if you don't practice both, these are perishable skills. So it's even for myself. That's why I have this textbook. Sometimes I'll go back to the basics, try to understand it from a very basic standpoint or framework. That way, if I'm tasked with explaining something as a concept, which is a lot different than diving into the deep weeds of something, right? It's a lot more important to be able to distill it down into the most salient points, if that makes sense. But yeah, to answer your question, I'll post that later in the Slack channel. I think what you're referring to are like droplets or teardrops, something like that,
Yeah.
raindrop like points. This is actually a really good application for linear regression, something you may get into in this course for a little bit, or even touch on with respect to your final projects. What ends up happening is when you're visualizing these different residuals, when you have the difference between y true and y pred, so the actuals minus the predictions, you have this difference. These are the residuals or error terms, right? So you're plotting these residuals versus the fitted values for this regression. So you might see something that's a funnel shape or like droplets clustering at lower ends, and that means that there's not constant variance. So you have like another case where that's one example where you have bounded or censored data. So there's like a lot of zeros in the data. For example, income, not everyone has standard uniform income. There's a lot of variance there. Or time to event data, time to death is one of those examples. And if there's a spread above zero, it creates this like droplet like tail. So you're plotting confidence regions with these contour levels with respect to that. Now, for 3D shapes, now, does that answer that piece of it, or is that a little bit different than what you had in mind?
No, that's fine. And then I guess I wanted to ask in relation to CLT as well, the central limit theorem, like what happens
Yes, right. That's a
after?
good question. Yeah, central limit theorem is crucial in all of this. And as a jumping off point for statistics, especially inferential, you want to start off with a baseline assumption that distributions, if sampled with a high enough frequency, will maintain normality or a Gaussian. There's that Gaussian assumption in place that if you sample enough times with replacements, if you bootstrap it, you will see over time that the distribution follows that of a normal distribution, especially if you have at least 30 observation points, which is based on the central limit theorem. You have that Goldilocks number of 30, right? Anything below just doesn't quite meet that requirement. So you want to maintain that as much as possible to be able to compare different situations or scenarios across different time horizons, across different race and ethnicity groups. If you're assessing bias and fairness, this is where it's applicable. Um, it's applicable everywhere. So you want to measure it at a baseline level with respect to that central limit theorem. So every time you sample with enough high enough sample size, you're invoking that central limit theorem. You're basically repeating that assumption. Um, does that kind of answer your question?
Yeah. So yeah, I think yeah, in terms of the applications, so you mentioned income is one of them. Are there any other
Yeah.
applications where it can be used at? Like a 3D shape?
Um,
Because like for
well,
like a two-dimensional shape,
yeah,
like just a flat curve, like I
yeah,
can see applications for it, but I'm having
right.
a hard time
Yeah,
on seeing where it can be
yeah.
used in a 3D aspect.
See, that's an excellent question. This is beyond the scope of my understanding of statistical applications. I think you really have to get into like nuclear physics at this point.
Okay, so it's not for
Maybe, maybe not. Let's say if you're doing principal component analysis, and there's a certain level of dimensionality reduction that takes place. So you have this multivariate visualization schema, right, where you have these points plotted in the 3D, so you could easily parse which way the principal components are distributed. I mean, on the X and Y and Z axis, now it's 3D, right? And so in this case, the shape emerges from this latent structure in the data. Then you have another example, if we're talking about 3D shapes, where we're discussing joint distributions, for example, you can have bivariate, trivariate, probability density functions or kernel density plots. But when you take that 3D blob, because at the end of the day, you can call it a shape, but it's really a blob. It's not necessarily trapezoidal or rectangular, whatever the case is, right? It's a blob, just to generalize it. You don't know if there's normality, non-normality, what the correlation is, or the type of distribution. It could be mixed. So this is when you have joint distributions because they're not necessarily all standard or normal. That's just an example. What you were asking, I don't have a specific example of an actual application in industry for something 3D. Like, are we talking strictly statistics or just 3D analysis of shapes and data in general?
more in the scope of machine learning and artificial intelligence. I was
Hmm.
wondering if there's
Yeah,
anything
yeah.
in that scope there.
Oh, yeah. It's an excellent question. This is something that they don't teach very often. Let me let this person in. Give me a sec. Something they don't mention very often in within the scope of machine learning or data science, as a principle, as a rule, as a foundation, as a discipline. More importantly, is something that only I have worked with maybe once or twice, and that would be the partial dependence plots. If you have a chance, I would recommend you pull it up in scikit-learn. So you can take the two most important features. If you're doing feature importance, once you pull out the best model that you have, right? And you want to look at the rank order of those features. You could do that through a random forest model, just get the feature importances, right? You could use SHAP analysis. You could do a waterfall plot or sorry, B swarm and see how much importance is weighted in terms of each feature, right? You could do it like a more granular analysis that way. And I'm getting to your answer. And or you could just take straight bar graphs that trickle down in order of importance, and you can see from there what are like the, let's say, pick the top two, right? Top two features that carry the most weight in the model. And you would take those two features and plot them on a partial dependence plot. And on a 2D layer, you can see how, generally speaking, which way, what happens if there's an increase in one feature, does it affect how does it affect the other feature, does it decrease, and so on and so forth. But when you plot that in a 3D, you can spin it around and it becomes multi-dimensional. So that's another application. I think that would be very important, and it would definitely give you guys, I think, an edge as data scientists or artificial intelligence practitioners, because not from what I've seen, not very many people take it to that layer of that depth of analysis.
Does it assume that the features are linearly dependent, and what happens if they're not linearly dependent? They're important, but there's no relation. There's no linear relationship between them. So the feature dependency plot, would that work?
Right, and that's a great question, because they're also known as, I'm just looking at the documentation. I can pull it up for you guys so you can see it. And it's very important to read through something like this in scikit-learn, understand the scope, understand like what it's used for. You don't want to just plug something in and plug. I mean, I understand a lot of people want to use ChatGPT and LLMs, and that's fine. I'm not against it. I'm 100% for it. I just think that if you're a little late to the game where you haven't learned it in a classical way, and that's all you're doing is using it, it becomes very tempting to just get the answers, plug and play, plug and play. And one day when you're working somewhere, they're going to ask like, well, how'd you come up with this code? What does that line mean? And if you can't explain it, they're going to know that you picked it up from somewhere else. And we can get into that a little bit later, but there's a lot of bugs that can come out of code that you copy and paste from there without understanding it. You may not see it right away because a bug isn't necessarily an error. It could be a logical bug. It could be if you're dividing something instead of multiplying it. Well, it may work for like 3 iterations of the data set, but then when you test it on 10 other versions of that unseen data, suddenly there's drift, something changes, and it's supposed to be generalized. I'm just throwing out an example, and it's not really multiplying or dividing. There has to be a rule in place, or maybe like an if-else condition based on certain criteria. LLMs won't give you everything. They'll give you a good chunk of code, but you have to understand the logic behind the code and what you're trying to do. Now, the reason I bring all that up and I'm front loading my answer to you in this scope, within the scope, is because, like, for example, take this, what I'm about to show here. I have an example here. I built a library with a colleague of mine. Let's see here. Yeah. Actually, I moved it to a different one, model metrics. You guys are more than welcome to use these for your projects as long as I get credit, we get credit for it in your citations. But you can pip install them from just like you would any other library. So this one's called model metrics. Here's some examples of 3D partial dependence plots. So if you take like a housing example, this is publicly available, California housing, you can train just a quick model gradient boosting regressor for regression and pull out the features, get the top. I mean, here in this case, you're plotting all the features at the 2D level. But if you want to take the top two and take it to the 3D, what you end up having is something like this, right? But you can't really pivot it and move it around. But this gives you a little bit of insight in terms of the how house age and average occupancy works. So as average occupancy increases, you see at this very high end, you have a higher number associated with house age. So here you can move it if you want to do like plotly plot, you can move it around pretty much. Yeah, this is all available through the library. I don't want to spend too much time on this. I think we should go over the quiz and some other things, but do you guys, does that kind of help with
Yep, thank you.
You're welcome. I think you also mentioned something about skewness as well. Am I not mistaken?
Yes.
It's very common. Like income is an excellent example. Bias and fairness, things like that. I mean, not every single race group, ethnicity group, sex group, social vulnerability index. I mean, name a sensitive attribute, whatever the case is. Not everything is going to be equal across the board. So you have skewness, and it could be education level. It could be a bunch of different things. That's why we have sanity checks in place. We don't just pass models into production without assessing bias and fairness, without assessing how the model performs across different sensitive attributes. So skewness is a real thing, and it's good to see if that skewness is asymmetric. If the distribution is asymmetric, you have skewness. Maybe there's a way to see if the differences between two groups. One is the reference group. And so, for example, in race, you can see the reference group is white, and the other group could be like Asian or something like that. And if there's a difference between the false positive rate, for example, of one group over the reference group, you have what is the disparity metric. So you can see, are those differences statistically significant? And that's when we use stats. Is there enough there to make a claim that there is a statistically significant difference? Otherwise, you fall back to the null. and there aren't any statistically significant differences, but you have to establish what that statistical test is. And skewness happens very often. I mean, it could be right-tailed or left-tailed. If the mean is greater than the median, you got a right skew. But all of this affects the assumptions that you have with respect to all of these different kinds of parametric tests. You have your standard t-test, you have your analysis of variance, and so on and so forth. Something that we don't get into in this course, and as a data scientist or even AI practitioner, I would be hard pressed to see anybody using something like a box Cox transformation. It's just another way to normalize the data if you're doing inference, when you're doing inference rather. But skewness is a thing and it happens, and there are ways to deal with it. So let's end with that and let's go to the quiz. If that's okay with you. But yeah, that's all I have. That's all we have for the quiz. Is there anything for the next, give or take, half hour you guys want me to discuss? I see a question here. Is there a hand raised?
Okay, I got a question.
Sure.
Of all the hypothesis tested out there, the chi-square, F, ANOVA, um, which are the strongest ones that are you would encounter in AI? I know it's probably going to change given the different applications. You know, like I'm coming from meteorology, and a lot of those are, you know, we have to do multiple of them to try to find, you know, feature rankings and tests like that. But which of them are the strongest one that in your opinion, that you come across?
Uh, it's a great question. Just a minor correction. I think you're referring to statistical tests. They're different than hypothesis tests.
Yeah, sorry. Yeah, yeah.
But yeah, you're gonna see all kinds, yeah, and there's no way you'll ever remember every single one unless you work with them daily. Like all you do is stats. But there are some like the Kolmorov's Smirnov test, the KS test. Otherwise, like if you're comparing two distributions, like you take a model versus reality, or fairness, like I was discussing. Uh, some of the strengths are, what can I remember from it? It's non-parametric. Uh, that's I can remember that much. And because data drifts, because you have a data set today, is not going to necessarily be the same data set a year from now, right? When you do a look back retroactively, or not prospectively, the opposite, you might say, oh, this changed, right? So that's drift. So
Right.
it's really useful for detecting drift.
Mhm.
That's one example. Then you can do different types of permutation tests or randomization tests. They don't all have to be specific statistical tests. Chi-squared, okay, you can never go wrong with the classic t-test when you're just comparing a difference between the observed mean and the population mean. You're dividing it by the standard error.
Mhm.
That's used very often. Then the chi-square test is especially useful for just, sometimes it's not the advanced statistical test that wins. It's a basic chi-square test where you're looking for, you're testing independence between categorical variables. It's
Mhm.
interpretable, it's fast. Uh, if you're doing some kind of feature association analysis, or
Mhm.
again, fairness audits, survey analysis, very popular with survey statisticians or whatever their
Mhm.
titles are nowadays. And another popular one is like Man Whitney U,
Mhm.
Wilcoxon's signed rank test, just to name a few. But
Yeah.
that's a great question. I would, yeah, I mean, a lot of this stuff is available through SciPy stats. Matter
Yeah.
of fact, there's a conference for SciPy coming up. You guys might want to attend since you guys have been working in statistical analysis using Python. If you guys are really interested in the statistical applications of data science or AI, I would definitely see if you could attend the SciPy conference that's coming up. Look it up and the dates and all that kind of stuff. Anyone else?
A quick follow-up to that.
Sure.
So, is there like a basic standard process once you know your data and you say, okay, I've eliminated all of the dependence and it's everything is as independent as I can make it, right? It's categorical. I know a lot of my data, and I got a whole suite of tests to choose from. Is there a standard process? You know, like okay, go from this test and then move up this test or something like that?
Not every test is going to be applicable. That's why you always have to check what the underlying assumptions are, and what the strengths and weaknesses are. Like
Okay.
as they say in B school, right? The SWOT analysis, the strengths, weaknesses, and opportunities and threats. Right? So,
Yeah.
that's a great question. Yeah, but like you can't really run a chi-square test on quantitative data. It's more
Mm.
about categories. So you have to assess what kind of data you have and what you're looking to achieve with it. So
Okay. All right.
yeah.
Cool. Thanks.
At the end of the day, though, no, that's an excellent question. You are calculating a p-value, and you are comparing it to a significance level alpha, and that's going to tell you whether or not your results are statistically significant. And that can bring about all kinds of other holes, if you will. You know, what's the false positive rate associated with this? Is there a type 1 error that there's a certain number of false positives that could be mitigated by um, a lower significance level, like bringing the alpha down from 0.05 to 0.01, or even a type 2 error where you just don't have enough data. That's key in statistics. You want to make sure you're sampling with enough data. So if you don't have enough data, you might introduce more false negatives. So you just increase the sample size.
Okay.
Anyone else? Any questions on the final projects or the homework or something like that?
Yeah. I just wanted to check in regarding to as far as model selection is concerned for the final
Right.
project. The models that we're going to select, because we discussed this with my teammates, the models that we're going to select, does it have to be within the course, or we can explore different kind of model analysis or model selections?
That's a great. You guys are just killing it with the questions today. I love it. This is
Yeah,
this is what makes
I
it
just
strong.
wanted to make sure I know the boundaries.
No, absolutely. This is great. This is really good. Um, I would say definitely don't take it too far. It's an introductory course. Like, I mean, by too far, I mean you can run the logistic regression if you're doing. So, like, if your problem is binary classification, you could always make you could always formulate a problem to be that of binary classification. If you distill the outcome to 0 or 1, yes or no, or something going to happen or something not going to happen. Is a condition met or is it not met? Right. So,
Mm-hmm.
based on algorithms like the random forest model, the logistic regression, XGBoost, any of the tree-based classifiers, any of the boosting algorithms, anything that deals with binary classification, yeah, go ahead and use it. If it's in scikit-learn, I don't mind, right? Test a few of them, have fun, enjoy, see how what your AUC score, the F1 score, well, what else comes out of it? Like precision, recall, specificity, all that good stuff. Everyone always looks at accuracy. I'm just going to tell you right now, accuracy is not the most important thing when it comes to a model's performance. It depends on the problem you're trying to solve. Because if you are trying to figure out the presence or prevalence of a disease and model that, right, you might want to look at average precision as a metric of interest, right? Why is that? Let's look at precision, right? When you're looking at anything that's related to precision, you have, by definition, your true positives over the true positives plus false positives, right? So what happens if you have a lot of false positives, and we were just talking about that with respect to the type 1 error, right? What ends up happening is you end up lowering your precision, because when you increase the denominator, it drives that metric down. So if you have a good solid metric like precision in healthcare, for example, you have less false positives, like the higher the precision is. That's just one underlying assumption. That's kind of how I want you to look at these metrics and understand what's more important. Accuracy by itself is just an overall picture. What is accuracy, right? Same thing with area under the curve, AUC. It can give you a good gauge for how well the model is performing holistically, but you do need to look at the trade-offs between recall, where you take the true positives divided by the true positives plus false negatives. So in this case, if you have a lower sensitivity or recall, you really have a lot of false negatives, more on the type 2 error side.
Okay.
But to answer your question more directly is, name a model what did you have in mind exactly?
We're still talking about it, and
Right.
linear regression, and we have we've given ourselves a few assignments towards one another to do further analysis based on like for model selection, but we just wanted to be sure that okay, can we go outside like out of what we learn in the course, explore some more, or do we stay in what we know in the course? That's what we wanted to.
Right. Yeah, I would stay within the confines of the course, maybe use like some of the models that I mentioned. They're machine learning models, although you could make logistic regression a statistical model if you use the stats
Mhm.
models package for it. It doesn't have to be anything crazy or fancy. If your problem is regression, test linear regression. Like
Okay.
if it's a continuous regression, not logistic where you're doing binary classification. You could also test something more fancy like XGB regression or lasso regression. Those are all suited for continuous outcomes.
The part about the models that are covered in the course, and I totally understand that, that makes sense. However, at this point, and we're still, basically, the team is trying to, like research what the different models are that are available. But
Yeah.
at this point in the course, we haven't covered any of these models.
Of course. Yeah.
None that
Yeah.
you actually mentioned, like
Yeah.
not even linear regression. But we haven't
Yeah.
covered classifiers, or you mentioned what is it like? See, like I can't even recall them from memory because their names are so alien to me. So
We did cover regression, to be fair. Last time I went over an example in Excel.
yeah, no,
That was
regression.
yeah.
We did, yeah. Okay,
Linear
so
and continuous.
okay, so I guess since we are sort of looking for what we're giving each other like assignments about what to research,
Yeah.
whether this or
Yeah.
that model would be appropriate to analyze our data
Yeah.
set.
Yeah.
Like for example, you mentioned classifiers. So classifiers
Yeah.
are a type of model, and those are going to be in the course.
No, not all these models are going to be in the course, but as all you need to know for this course is like again, what is your outcome, right? So you understand what your feature space is, you know what your variables for your predictors are, right? Let's say what's your data set? Give me that much.
Likelihood of credit like of a account holder to default on his loan.
Yeah, that's a classification problem right off the bat because there's either yes default or no default, right? And that's a
Correct.
binary classification problem. That's not a multi-class classification problem. You're not putting that's too advanced for this course. It's not. I don't even not that's not used very often. It's used, but I mean you could break it down into different groups like likelihood of default, this category, that category, the low default risk, high default risk, medium. No, you're not doing that. You're just saying is the bank card holder, whatever the case is in the banking industry, a row it represents one person, right? We all agree with that.
Yes.
So that row is either it's gonna have a bunch of features. It's gonna say income. I'm making this up. I think I've seen that data set before. I'm throwing just random stuff out there. Education, some
You're correct.
quantitative. Sorry.
No, that's correct. You're correct with,
Right.
with the
A few
classification.
others, right? They're like
Yeah.
500. I don't know how many features it has. Those are all your X sub 1, sub 2, sub 3, and so on and so forth. These are your features. That's your feature space, your matrix, right, of features along with the rows that belong to all the different cardholders. Then you have one column that will tell you yes or no currently. Will they default or not? Have they defaulted or not? You don't know what's going to happen in the future. So if you have enough data, hopefully there's like at least 1,000 observations. What you do is split into, let's say, 800 training. So you're going to train the model in 800 of them using the train test split. And 200 of them you're going to take away and use it as your holdout set. And you're going to predict on that holdout set. Because that holdout set is your unseen data, supposedly. Because that's how you test the model. And when you, let's say you get good results with the different metrics I mentioned, later down the road, you could test it on additional unseen data. And the expectation is that the performance will stay about the same. Of course, no one knows how that goes until they see the model in deployment after a certain number of iterations. But just to answer your question, it's fair that you ask, like, well, we haven't learned any of these models, but I'm suggesting to you is that you don't have to do anything fancy. If you want to, you can go all the way through XGBoost and test a bunch of different models. For something like this, a simple logistic regression model, which I do believe is covered in the textbook, and it's on scikit-learn. And I explained the structure before. Maybe next session, what I could do is give you a small example of how to predict using a classifier. You just simply take that, you import it from sklearn.linear models import logistic regression, and you have your X defined, right? Those are all your features. So X equals, you read in the data set first, then you can parse it. You take away, like do a dot drop, take away the column that's your outcome and pass that into Y. So now you have your X, now you have your Y. Then you do the split. Once you do the split, now you have your X test and your Y test. So now your data is partition accordingly. You have 800 dedicated to X train, Y train, 200 dedicated to X test, Y test. And that's if you do the 80-20 train test split, 80% to training, 20% to test. Otherwise, popular choices are like 70-30, depending on the size of the data set. There's no right or wrong answer. There just has to be a sufficient number of rows allocated to the training set. And then you run the classifier is already there, so you just use the classifier to do the predictions. So you don't necessarily have to know all about what this classifier is doing in this course. Like we're not, that's what the rest of your program is for, I would imagine. Machine learning is part of it, right? You're going to understand more about what are tree-based classifiers. Like, so what I'm saying is I don't care if you like don't understand that an XGBoost model is agnostic to missing data. I don't care. You can fill the missing data yourself and still run the XGBoost model. As an example. So what I'm saying is you don't have to know how the models work with different kinds of data. If you're using a classifier, just use it. And you don't have to me, like I said last time, I don't care if you run, give like 2 models a shot. If you can't do more than 2, at least 1 model, but at least try at least 2 different models. And
those
that
models
should be more than enough.
Those models will be covered later in the course, or we're talking about models that are not covered?
Those models are probably not covered in the course. This is a statistics course, which is why, again, I'm saying you don't have to use them unless maybe some of you guys have experience with them already. We have
Okay.
people here from diverse background, but a simple logistic regression, linear regression, that kind of thing, I think is covered somewhere in the book, and you can Google it if you guys want. If you really want to take a session just on some modeling, basics of modeling stuff, we can devote some time for that.
Okay, thank you. Beakal, does that answer your
Yeah.
side of things?
I'm good. Yeah.
Cool.
Maybe we could take this offline, Max. Logistic regression might seem. Yeah, we'll see. Yeah.
Believe it or not, sometimes even in fancy healthcare deployments, sometimes it's just a simple logistic regression model is the one that does it all.
Yeah.
There's the gold standard kidney failure risk equation that was written by Tangri in 2011, I believe, uses a logistic regression model. And that's to tell if patients are the risk profiles for patients given their age, estimated glomerular filtration rate, and urine albumin creatinine ratio, and different features that relate to kidney disease. To what's the probability, like percentage wise? There's a calculator online that does that. I wrote a Python library replicating that. So that's off a logistic regression model. And anyone, what you don't learn in school so much, and you kind of learn on the job, is that you do start to move away a little bit from just plug and play, and you can use someone else's probabilities or at the end of the day, that's what you're doing when you're getting a model. You're extracting the y proba or the predictions or the zeros and ones or the predicted probabilities. When you have the predicted probabilities for each row, you can literally assign based on, depending on the threshold you use for the model, the standard one's 50%. What is the likelihood that they're going to get that condition, 0 or 1? That's the output of the classifier at the end of the day. You're looking for that probability. That's the statistical side of it. But that's something that's outside the scope of this course. But I'm just saying that the goal is to get you to think outside the box a little. Otherwise, no, like most of you have done just incredibly well on these assignments, discussions, and I'm definitely going to speed it up again. I know everyone's worried about the grade, but I'll tell you what, historically, everyone's done pretty well. So mostly. So keep it up. If you have any questions, shoot me an email or put it in Slack. And we as much as we try to be, as much as we try and strive to be perfect, we always fall short, but that's the nature of the business, education. And so like we want you guys to become so good at this stuff that you can come back and teach it and become the strongest AI practitioners out there. So that's the goal of this program. If there's nothing else, I think we'll just go ahead and call it a day. And any last minute thoughts, questions? All right then. So take care. Have a wonderful weekend. I'll see you all soon.